Okay, bear with me here. This is going to be a little rough going. I don't have a lot of time to do this, but I want to make sure it gets done for you guys. So this is your classification pyramid, and this is our first chapter. This is kind of a puzzle that I wanted you to solve. The N is for no. So if you look at the pyramid, no, yes, no, yes, no, yes. B is for element, so we can cross the B off. And then J rather is the mixture the same throughout? Okay, so what you can see then is this narrow area is a question. If you remember anything about the pyramid, then this area would also be a question to divide up these two, and then of course this area here would be a question to divide these two. Okay, so if you look at J, it says is the mixture the same throughout. If you just think about it for a second, then what you're going to be doing here essentially is you're going to be categorizing the two types of mixtures. If the mixture is the same throughout, yes, it's going to be a homogeneous mixture, so that's going to be letter H. If the mixture is not the same throughout, what that means is you're going to have pieces and parts. You're going to have a heterogeneous mixture. Okay, so if you just think about this a little bit, when we classify matter, what we're doing is we're first initially categorizing into two separate areas, either mixtures or pure substances. So once you see this mixture thing here, then what you can deduce is that this area is going to be pure substances. So let's just work up to the top. If this is a classification pyramid, obviously at the top we're going to have all matter. How do we separate then into pure substances and mixtures? Well, the answer there is going to be, can the matter be separated by physical means? Okay, so physical means would be things like sorting, sifting, straining, using a precipitation technique, decanting, all of those things. Okay, so if you can separate the substance out, it's a mixture. If you can't, well, what you have is a pure substance. Okay, so all we've got left here then is to figure out what goes in this box really. So if this box over here is an element and it says no here, then what happens is that this would actually be a compound in the next box. Okay, elements and compounds are both pure substances. So what's the question then? Well, it's the only thing left. Can the matter be separated by chemical means? And that's the same thing as saying, can you decompose the substance chemically with ordinary chemical means? Okay, so this is review. It's kind of put in puzzle form. I did flip-flop it a little bit to force you to think. Okay, sorry about that. I flipped over to this PowerPoint here now because I have some of these things on slides to allow me more room to write. So here we go. The next problem here, number 2A, is a conversion, and you're going from centimeters to nanometers. So here's the deal. When you're going from centi to nano, I want you to use two conversion factors. So you have to know two things. One of those things that's going to be helpful is to know how many nanometers are in a meter. That would be obviously the thing that's going to be the most obvious. So 1 meter is equivalent to 1 times 10 to the 9th nanometers. And yeah, I would expect you to know that since we did all of those conversions on the electromagnetic spectrum. I know a lot of you took shortcuts, but you really just need to know this. 1 meter is 1 times 10 to the 9th nanometers. And then what would obviously be something that would be good to know is that a meter is equivalent to 100 centimeters. Now I know that you could do this with one conversion factor. 1 centimeter is equivalent to 1 times 10 to the 7th nanometers, but I wanted you to use 2 because it's good for you. So we start out with 55.7 centimeters. And the first thing we're going to do is to convert that to meters using this equality right here. So we have centimeters on the bottom, meters on the top. That'll cancel out centimeters. We go for our bigger unit. We put a 1 in front of it if at all possible. All right, and then we have 100 centimeters in a meter. So that gets rid of centimeters And then what we have to do is we have to go from meters to nanometers. What's bigger? A meter. How many nanometers? 1 times 10 to the 9th nanometers. All right, so that gets rid of meters. Do not reach for your calculators. All you have to do is look at this for a second. Besides the 55.7, everything else has to do with ones. There's really not any tough math here. So if you take 55.7 and you divide it by 100, essentially that's going to give you 0.557. No brainer. Then all you have to do is look for exponents. You only have one, so it's going to be times 10 to the 9th. It's a numerator, so you just keep it as a positive 9. Now, we know that's not correct scientific notation. You have to move your decimal over. It's going to be 5.57 times 10. Your coefficient became larger by a power of 10. Your exponent becomes smaller by a power of 10. And your unit is nanometers. Okay, so this is something that's not too hard. You might be a little rusty on it. Just make sure that you review it. Okay, the next conversion then is to take micrometers and go to kilometers or micrometers. All right, so I said again, use two conversion factors. So what do we know? We know that 1 kilometer is equal to 1,000 meters. And yes, you should know that. And we also know that 1 meter is equal to 1 times 10 to the 6th micrometers. That's a mu. All right, so if we know those two things, we can just start this process. 6.09 times 10 to the 8th micrometers. And the first conversion factor we want to use then would have to involve microns. So that would go on the bottom, meters on the top. What's bigger? Meters. You stick a 1 there. And then there's 1 times 10 to the 6th microns in a meter. Okay, got rid of those. Now, what we do is we simply move on. We go from meters to kilometers here. Meters has to go on the bottom to cancel. Kilometers is going to go on the top. Kilo bigger, 1,000 meters in a kilometer, or 1 times 10 to the 3rd meters in a kilometer. Okay, now the reason I switched this over is because if you look at this, what would end up happening is our exponents on the numerator are going to total up to 8, and on the denominator they're going to total up to 9. So essentially what you're doing here is you're subtracting 9 from 8, and that gives you a -1. Okay, so if you look at this whole thing, we just did all the math. All right, so this is going to be 6.09 times 10 to the -1st, and it's going to be kilometers. And since this decimal is right here, your coefficient's between 1 and 9.9 repeating, what that means is you don't have to adjust it. Okay, so this answer is good to go. If you want to take it out of scientific notation, no problem, because it's a reasonable answer to put out of scientific notation. Okay, the next one is a simple density problem, and what we have to do first here is we got to read it. We want to find mass, we have a volume, and we also have a density. Here's my density. Okay, and we want to know the substance in the end, which takes a little bit of legwork. Okay, so what do I need to do? First of all, I need to list. Okay, so I want to know the mass. My volume is equal to 83.8 milliliters, and my density is going to be equal to 2.71 grams per milliliter, which of course is the same as a cubic centimeter. So the density equation, never forget this, the density of a substance is equivalent to its mass per unit volume. Alrighty, so density equals mass per unit volume. So that would mean if we're solving for mass, we would simply multiply both sides by V, and we would get M equals D times V. It's as easy as that. So we go ahead and solve. M equals, okay, your density is 2.71 grams, and I'm going to put milliliters on the bottom here, and you're multiplying that by the volume, which is 83.8 milliliters. Okay, so I left my answer key at school. I'm going to go ahead and chunk this out right now. 2.71 times 83.8. And on my calculator, I have about 227. I'm going to look at my sig figs. I have 3 and I have 3. So I'm going to go ahead and just go with my mass as 227 grams. Okay, so how do I know what substance this is? All I do is I take a table of more common substances. It is a pure substance. I didn't tell you that here, but I thought I had. At any rate, this material is going to be aluminum. And if you didn't get it, don't worry about it. I just wanted to have you guys challenge yourselves and think about this, okay? And aluminum, of course, is a very lightweight metal. Okay, the next problem, these are pretty easy except for one's a little bit tricky. So number 4, this first one, if we want to put 7,800 grams into one significant figure, the first thing we would have to do is we would have to round this 7. Okay, so since we have an 8 next door, we'd round the 7 up and we'd have an 8. So this would be 8,000 grams in one sig fig. Now, I'm going to skip this one and come back to it. So on the next one, we have 7,800 grams, and in 4 significant figures, what I would have to do is just simply stick a decimal point here. And what that would mean is that this is a significant figure as well as the rest of these. Okay, now don't lose sight of the fact that significant figures are definite, measured values with one uncertain digit tacked on the end. So this arrow is pointing to my uncertain digit. What that tells me then is my range here conservatively could be about 7,790 grams to about 7,801 grams, or maybe a little bit more off. Okay, up here what I'm saying is that my range, because my 8 is one significant figure and that's uncertain, then my range could be really anywhere between 7,000 and 9,000 grams, or 7,000 and 8, maybe 8,000 grams, maybe 9,000 grams, who knows. It could be very far off, but you can see it's not measured very accurately with an accurate measuring device, so it could be fairly far off. Now 5 significant figures at the bottom here. Most of you will get this pretty quickly. Don't forget, you have to tack another 0 on. So that leaves us with this second one, 3 significant figures. The only way that you can do this is by putting 7,800 into scientific notation. You cannot say 780. That's not anywhere near 7,800. You cannot put a decimal here. That doesn't work either. That's 4 significant figures and it has nothing, it's nowhere near 7,800. So what you have to do is you have to save this, and this number. And so you stick it in scientific notation at 7.80, and then boom, 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 times 10 to the 3rd grams. 3 significant figures here, and that's the only way you can get around this. Okay, on these next problems, I'm not going to do the math, but I am going to show you how to solve for these. After you add these 2 numbers up, what you have to do is look at it for a second. Okay, you're going to get a value that goes to the thousands place, there's no question. However, your answer, remember, if you're adding or subtracting, your answer cannot be any more precise than the least precise measurement going into the calculation. So since this measurement here only goes to the tenths place, this is going to limit your answer. So when you go ahead and you add this up, then you are going to put your answer to the tenths place and you're going to round accordingly. Okay, so don't forget that addition and subtraction, you don't count up how many significant figures there are, you look at the place value. Now here you're multiplying, so you can now count. You have 5 significant figures here and you have 4 significant figures here. So the rule is when you multiply and divide, you go with the value, or you go with the least amount of significant figures. So whatever you happen to get here is going to be in 4 significant figures. And I will be posting those answer keys eventually. Okay, so a couple more problems here. And this is a division problem. So if you just check this out for a second. Division, you're going to be counting significant figures and you're going to be subtracting exponents, 8 minus negative 2. So I'm not going to do the math here, but once you divide, 6 divided by 5 is roughly going to be 1. All right, so you're going to have 3 significant figures, so there they are, 1 point something something, and your exponent then is going to be 8 minus negative 2, which gives you an exponent of 10. Your units then are meters per second. Okay. Now the